Okay.
Thank you very much for the introduction, Mr. Garcia. My name is Hoon Hyung, and I'm from LG Chem, LG Water Business Solutions. And actually, I'm based on Los Angeles, California, so I flew like 18 hours from California to here. So I think that shows, our commitment for this conference, also for the, Spain, membrane market. And of course, our sales director, Juan Carlos, are working hard to work with you guys here. But today's my presentation is about the boron removal in a thin film nanocomposite membrane in seawater desalination. Before I start, let me go through quickly about LG Chem and LG Water Solutions for someone who are not familiar with our company. So, who is LG Chem? LG Chem is probably about LG, right? LG like electronics. So mostly know about LG electronics, but might not be familiar with LG Chem. So LG Group is a global conglomerate based on Korea, and it has like $140 billion US dollar sales revenue annually, and have $2.25 million employees. LG Chem is the subsidiary company of the LG Group. We have $21 billion revenue. US dollar, 21 billion US dollar revenue in 2014, and we have almost 20 million employees throughout the world. And we are the third largest chemical company in Asia, and 13th largest in globally. LG Water Solution is business group under LG Chem, and we produce nano H2O thin film nanocomposite reverse osmosis membrane. We have headquarters in El Segundo, just right next to the Los Angeles, California, and we have like a main manufacturing facility in Cheongju, Korea, South Korea. Nano H2O is founded in 2005 in UCLA, University of Los Angeles, California, as a startup utilizing nanocomposite membrane technology. And commercial production was started in 2010, and a commercial manufacturing facility was built in 2010 in El Segundo, California, and commercial production was started in 2011. 2014, LG Chem acquired Nano H2O. Now it is like LG Water Solutions, and a new manufacturing facility in Cheongju, Korea is built in 2015, just a couple of months ago. This is based on the GWI desalination market report released in 2015, actually. This is the size of the membrane market share since 2010. And Nano H2O has 4.4% of the market share at this point. But this is pretty small market share. But if you think about the fact that the company started in 2011, mass production in 2011, and how conservative all the engineering companies are using like a new membrane. So considering that fact, I think we did a pretty good job to penetrate into this membrane market. We have so far almost 400 installations over 50 countries, and we have like sales offices throughout the world. So let me talk about the issue of the boron rejection in seawater desalination. So before 2009, boron regulation for drinking water from the WHO guideline was 0.5, and it was basically a limiting factor for the seawater desalination plant design. So most of the design is focused on meeting that 0.5 ppm of the boron regulation. But 2009, WHO raised that in guideline as 2.4 ppm. So many people think that boron issue will be pretty much gone, but that was not really the case, because some of the application requires more stringent boron rejection, mostly because they use this seawater desalination process or product water for the irrigation or to raise the crops. Those application require much lower boron concentration. So, for example, in Spain, we saw many projects where the project still requires boron concentration of 1.0 ppm. In certain area outside of Spain, like for example in Singapore, the project requires 0.5 ppm of boron, and even in Israel, they have a more stringent boron requirement of 0.3 ppm. So in those areas, some of the project, boron is the limiting factor for the system design. There are several other parameters, you got to meet for the drinking water guideline or some of the application guideline, but TDS or chloride, compared to these cases, TDS or chloride probably will be easier to meet. So many projects in this region, boron is the limiting factor for your system design. So typical, SWRO membrane has pretty good removal of the, ionic species like sodium chloride, so mostly like 99%, more than 99% of the rejection. But the typical boron rejection of the CORO membrane is pretty lower than, the other ionic species, mostly like 85 or 95%, depending on the, membrane grade, like BWRO or SWRO membranes. So typical method to improve boron rejection is because maybe sometimes with like a 95% or lower rejection, you can it is very tough to meet that the boron regulation. So typical method to improve boron rejection have been pH adjustment of the feed water, or you basically need to establish double pass system design. So why this outer membrane has lower boron rejection? So this is just a schematic of the membrane and the feed side of the membrane and the permeate side of the membrane. So in natural conditions, boron exists in form of boric acid and borate. And that species are determined based on the pH. So pKa1 is 8.6. That means if the water pH is less than 8.6, most of the boron species exist as H3BO3, so boric acid. And if the pH is higher than 8.6, it will be borate. So borate has charge, negative charge, but boric acid is basically neutral. But the outer membrane has like a negative charge. In nature, most of the membrane, most of the membrane available in the market, no matter what manufacturer's membrane you use, probably it will be different, like a range. But most of the reverse osmosis membrane in nature has negative charge. So borate has relatively good removal, but the boric acid is less removable because most of the borate are removed by the charge repulsion of the membrane surface, with the membrane surface. So typical seawater pH is ranged between 7.0 to 8.0. So that's why boron and most of the boron exists as boric acid, and the outer membrane has lower boron rejection. So in this section, I'm going to show you the performance of our membrane, nanocomposite membrane, regarding boron rejection. So this table summarized the actual membrane performance in most of the seawater desalination plant. We applied our membranes, and most of the references are in Spain. There are a couple of from the Israel. But as you can see, our membrane shows pretty good removal of the boron, which is pretty lower than 1.0 ppm. There are a couple of cases where we have like higher boron rejection, higher boron permeate boron concentration, but that is because we use those membrane for the second stage auto treatment. So to verify the actual boron removal of our membrane, our COR outer membrane, we did some pilot testing in Spain. The plant is located. The plant is San Pedro del Pinatar 2 SW outer plant located in Murica, Spain. And the test condition was this is pilot scale, so we just use one pressure vessel with 7 elements with our standard SW auto 440 scale for membranes, and permeate flow is 3.0 cubic meter per hour with 45% of the system recovery. So this is flow diagram of the actual plant. So basically, this is conventional SWRO system, which you have like DMF and a feeder pump and a high pressure pump. So we pretty much use the same feeder water to the existing full scale plant, and it's just sideline the feeder water to our pilot testing system and pumped with like high pressure pump to this pressure vessel, 7-element pressure vessel. So this is the membrane performance based on the pilot test. So feeder boron, and we have like a slight change in the operation condition, not so much, but this is to simulate actual full-scale plant condition. So we raised recovery a little bit and also membrane flux, but there are not much of difference in the operation condition. So as you can see, even if the feeder boron concentration changed from the 4.4 to 5.7 ppm, our membrane pretty much shows less than 1 ppm of the boron, and it even decreases as time goes by. Probably it's because of the membrane is more stabilized as you operate the membrane. And so based on the test data, we just back calculate what would be the element level in the boron rejection, because the data you saw in the previous slide is based on 7-element system rejection. So we just back calculated what would be the membrane rejection of boron based on the pilot testing result. So here you see that the range of the boron rejection based on the back calculation, and the result shows that pretty much our membrane shows approximately 94% of the boron rejection. And we, in our official spec sheet, we specify the 93%, but this is much better than what we specify in our official spec sheet. So in essence, you could achieve like 94% of boron rejection in element level. So how this like thin film nanocomposite membrane can get a better boron removal? I mean, I can explain you a little bit of background about our thin film nanocomposite technology and move on to the explanation of the boron removal phenomena. So this is pretty much standard procedure to make reverse osmosis, thin film, composite reverse osmosis membrane. You have like non-woven fabric, and you have polysulfone casting, and polyamide layer will be coated on top of the polysulfone layer. So you have basically, most of the outer membrane in the market has 3 distinctive layers. Like one is non-woven fabric, and a support layer of polysulfone, and then active layer of the polyamide. But the distinction of our membrane, like a thin film nanocomposite membrane, is we embed this nanoparticle in the polyamide layer, which nobody in the market has this technology. So we embedded this nanocomposite nanomaterial in this polyamide layer to improve the membrane performance. So one of the benefits of incorporating this nanomaterial in this polyamide layer is described in this figure. So as you can see, this one on the left is without a nanoparticle, and the right-hand side is with nanoparticle. So even we could achieve higher membrane flow with not sacrificing membrane rejection by incorporating nanoparticle. I mean, what usually happens during the membrane manufacturing process is if you increase membrane flow, you will lose some of the rejection, or vice versa. If you want to increase membrane rejection, you will lose membrane flow. So there is always a trade-off between rejection and membrane flow. But in this case, by incorporating nanoparticles, we can increase flow, but we don't lose like membrane rejection. That is the benefit of the incorporating nanoparticle in the polyamide layer. And based on this technology, we applied for the 27 patent application, and accepted 16 patents are accepted based on this technology. So another benefit of the when we go back to the boron issue, another benefit of this nanotechnology is this nanotechnology basically improved the boron rejection as well. So major impact of this nanoparticle is binding of the boron species to nanomaterials in the polyamide layer. So as I explained you, there are three distinctive layers in the polyamide membrane. And what's going to happen is that, let's say you have like boron species in your feed water and concentrate water. This boron basically bind with the nanoparticles embedded in the polyamide layer. And then this binding basically give better boron rejection, and this is the mechanism we kind of assume. This is not verified, but we assume this it probably will be the mechanism of the boron removal, better boron removal with a nanocomposite membrane. So membrane transport is just described by this simple equation. The solid flow is proportional to the solution diffusion coefficient and the total membrane area, and the difference between feed side concentration and the permeate side concentration. So what we explain, what we assume as the mechanism of the boron rejection in the influent nanocomposite membrane is boron species basically bind with the nanoparticles in the polyamide layer. And once binding site saturated with boron concentration gradient between the membrane surface and the concentration side will be lowered because of the binding site concentration with boron. So this lowered delta C concentration gradient promotes delta C result less boron transfer from brine to permeate. So so far we saw that the pilot testing the result and how our membrane perform in the actual condition, and some explanation on the how our membrane improved the boron rejection. So in the next section, I'm going to explain what is the impact of the boron rejection on the cost of the desalination in case the boron is the limiting factor for you. Okay. In case the boron is a limiting factor for the system design. So we did some simulation under the different membrane boron rejection scenarios. So this is simulation condition. This is pretty much standard, and average membrane age of 3 years. So this is 92%. We assume the three scenarios. One is 92% boron rejection, 94%, and 96%. 92% represent like previous generation reverse osmosis membrane, and 94% rejection, boron rejection is our membrane, which shows from the pilot testing. And 96% boron rejection probably will be the future generation of the membrane with like a higher boron rejection. So as you can see, membrane rejection is affected by several factors, but temperature is another important factor. So as you can see, for the 92% the previous generation membrane, it pretty much go above 1 ppm of the limit if the temperature goes above 23 or 24 degrees Celsius. But if we have like 96% boron rejection membrane in the future, probably you don't need to worry about boron rejection even if you have a very high temperature condition. So probably our membrane, 94% boron rejection membrane will be fine up to 27 or 28 degrees Celsius. But if it goes above that, probably we need additional measure to deal with the boron. So two methods can be considered. One is pH adjustment, adjust pH and raise the pH. And as I explained you, if you raise the pH, boron species will change into borate from boric acid, so you will expect better rejection of the boron species. And another way is you can treat in the first pass permeate further with the second pass, so that you can get the better membrane rejection. So pH for the pH adjustment, you basically need to use caustic, right? So caustic, this graph shows that how much of caustic you need to use to adjust the pH to obtain 1 ppm of the boron from the permeate. So if you have like a previous generation membrane, probably you gotta use up to 5.2 ppm of the caustic to deal with the boron. And in the current membrane we have, you gotta add boron from caustic from the 28 degrees Celsius and above, and probably up to 2.0 at temperature 32. That is kind of like a maximum we assumed for this simulation. But obviously, if you have like future generation 96%, you don't need to add anything. So this is the table comparing how much of the caustic you need to use to adjust pH and meet the 1 ppm of the boron. And for the partial double pass design can be considered to meet the boron regulation as well. So this chart basically compared how many of the membrane pressure vessel you need to produce 100 mLD of the product water. So what I wanted to compare was that, okay, we have like a current level of the boron rejection and previous generation of the membrane which has 92% boron rejection in the future. So if you compare this, for 2 meter 0.5 ppm per meter boron, I have a couple of slides, so I'm almost done. I'm sorry. Yeah, so if you have like a current 94% boron rejection product, probably compared to 92% the previous generation, you probably can save 5% of the pressure vessel. It's not exactly capex saving, but it is really related with how much of the space you need and how much of the pressure vessel and membranes you need. And if it is 1.0 ppm per meter boron, it will be like around 5.8%, 18.9 to 5.8. So that is like around 12% difference between a current generation, current membrane and the previous generation membrane. So obviously, if you have 96% boron rejection, you have like further reduction of the membrane pressure vessel. Okay, so in conclusion, with 2.5 ppm drinking water, still in certain cases, boron is kind of limiting factor for the seawater outer membrane system design, which determine the cost of the desalination. And the nano-H2 membrane, thin film nanocomposite membrane shows excellent removal of the boron in the field. And we verified the 94% of the element level rejection from the pilot test. And if we can, in the future, if you can develop the membrane with the 96% or above, boron rejection, it will change the, economics, or you can reduce the cost of the desalination dramatically. Okay, thank you very much, and thank you for your attention. And if you have any questions.